Welcome. This series explores plasma, ionized xenon gas under electrical discharge. Using inductively coupled plasma, or ICP, electromagnetic induction sustains it, producing light. Let's begin. This setup enables plasma formation and analysis. The linear DC power supply provides stable voltage, while the ModeRock ICP oscillator excites xenon gas inside the Pyrex globe. A PVC pipe and cotton cloth generate electrostatic charge, influencing plasma behavior. The Tesla gun initiates plasma formation with high-voltage excitation. A coil, wound with 104 turns of insulated wire, features a neon glow lamp that reacts to electromagnetic fields. The 7-watt UV LED excites phosphorescent materials, while the Yaesu transceiver monitors RF interactions. Finally, the HP monitor visualizes electromagnetic wave behavior in real time. Now that we've covered the equipment, let's examine the high-frequency oscillator, key to plasma generation. This high-frequency solid-state Tesla coil uses a self-tuned Class E MOSFET power oscillator at 10 MHz with a single-layer air-core coil. A Pyrex globe filled with xenon gas sits inside. Alternating current creates a magnetic field that induces an electric field, exciting and ionizing xenon to form a glowing plasma toroid. Next, we'll explore electromagnetism and its role in plasma formation. In 1820, Hans Christian Ørsted observed that an electric current produces a magnetic field, demonstrated by a compass needle deflecting near a current-carrying wire. This discovery opened new pathways in electromagnetism. After Ørsted's discovery that currents deflect a compass needle, André-Marie Ampère showed that electric charges in a wire generate magnetic fields, advancing electromagnetism. Next, we'll explore ferromagnetic materials and their role in magnetic field generation. Building on Ørsted's and Ampère's discoveries, this animation shows how spinning electrons form dipoles, creating magnetic fields with north and south poles. Opposite spin directions lead to opposite dipole orientations. Ferromagnetic materials contain electron spin domains that align to maintain north and south dipoles. When all domains align, the material becomes magnetized. The key difference between unmagnetized and magnetized materials is domain alignment. To understand excitation and ionization, let's review magnetic field generation. An electric current flowing through a coil produces circular magnetic fields. When loops stack, their fields combine into a concentrated central field, like a bar magnet. The right-hand rule helps determine field direction. Curl your fingers with the current and your thumb points along the coil's magnetic field, following Biot-Savart and Ampère's laws. Magnetic and electric fields interact dynamically, essential for excitation and ionization. The Ampère-Maxwell law explains charge oscillations generating magnetic fields, while Faraday's law describes how changing magnetic fields induce electric currents. Alternating current reverses direction, flipping the magnetic field, following the Ampère-Maxwell law. Yellow disks represent current flowing through the coil, generating a magnetic field shown by a black arrow. As current reverses, north and south poles swap, repeating in a continuous cycle. This principle is fundamental to electromagnetic induction, powering technologies like motors and transformers. As the magnet moves in and out of the coil, its changing magnetic field induces current, visible on the ammeter. This demonstrates Faraday's law of induction. Motion of a magnetic field through a conductor generates electricity. Ampère-Maxwell and Faraday's laws describe how electric and magnetic fields interact. Together they form electromagnetic waves, self-sustaining fields that propagate as transverse waves, with electric and magnetic components perpendicular to each other and the direction of travel. Transverse waves resemble pond ripples, Waves spread outward, but the water or fields moves up and down. Unlike electromagnetic waves, these ripples are mechanical, requiring water as a medium to propagate. Now let's explore how electromagnetic energy interacts with xenon atoms. The electric field plays the primary role in ionization, providing energy for electrons to escape. Free electrons then collide with xenon atoms, creating plasma. Each half-cycle accelerates electrons, further driving ionization. The magnetic field exerts a Lorentz force, making charged particles spiral, increasing collisions and ionization. Electrons in rarefied gas travel farther, gaining energy before impact. The animation illustrates how electric and magnetic fields shape electron trajectories. Imagine an ice skating rink with a circular boundary. The Lorentz force acts like the curved wall of the rink, causing electrons to follow a curved spiral path instead of moving in straight lines, keeping them within the ionization region. A cathode ray tube, or CRT, uses electric fields to accelerate electrons and magnetic fields to steer them. The Lorentz force bends their path, precisely controlling the electron beam, key to forming images on the screen. Next, we explore how xenon atoms interact with energy, examining excitation, phosphorescence, and ionization, key processes behind luminous phenomena. Xenon, a noble gas, has 5 electron shells, ensuring stability. Ionization occurs when energy surpasses the threshold, freeing electrons. In ICP, electric fields accelerate electrons, fueling plasma formation. Next, animations illustrate photoexcitation, how photons promote electron transitions. A photon, carrying a precise amount of energy, approaches an electron. Upon contact, the electron absorbs the photon, gaining energy in the process. An absorbed photon energizes an electron, driving it to the valence shell, a crucial step in atomic interactions and excitation. An electron shifts to a lower energy shell, stabilizing and redistributing energy, preparing for photon emission. An electron drops to a lower state, emitting a photon and releasing energy as visible light, the process behind neon signs and auroras. Glow-in-dark Lego discs absorb UV light, promoting electrons to higher energy states. Instead of immediately releasing this energy, electrons enter an excited triplet state, where quantum mechanical constraints delay their return, causing a prolonged glow, phosphorescence. This stored energy is gradually released as light, distinguishing phosphorescence from rapid photoexcitation in plasma. The upcoming video demonstrates this effect, showing how UV exposure enhances the disk's glow, visualizing phosphorescence in motion. Photoionization begins as a high-energy photon collides with a xenon atom, ejecting an electron and leaving behind a positively charged ion. To regain stability, the ion attracts a free electron, which moves toward the valence shell. Upon capture, the electron releases excess energy as a photon. This panel illustrates the first step, while the upcoming animations will depict the remaining 3 stages: electron ejection, attraction, and recombination. The electron absorbs energy and escapes, leaving a positively charged ion behind, a process called photoionization, key to plasma formation. The free electron binds to the ion, restoring neutrality. Energy quantization ensures a controlled transition, setting the stage for recombination-driven light emission. As the electron recombines with the ion, excess energy is emitted as a photon. This quantized release generates visible light, the foundation of plasma illumination. The 4 excitation stages show energy shifts, while the 4 ionization stages depict plasma formation. Photoexcitation energizes electrons, shifting them to higher states, while photoionization ejects electrons, forming xenon ions. Plasma formation is primarily driven by ionization, as charged particles accumulate and enable conductivity. An alternating electric field reinforces these transitions, intensifying the plasma glow. Xenon's full valence shell makes it chemically inert under standard conditions. Though its ionization energy is high, rarefied xenon has a long mean free path, allowing electrons to gain more kinetic energy between collisions, increasing the likelihood of ionization upon impact. Plasma, an ionized gas, exists in distinct forms. Cold plasma, seen in fluorescent bulbs, emits light as energetic electrons move through a relatively cool gas. Hot plasma, found in lightning and the sun's surface, reaches extreme temperatures as both particles and gas are intensely heated. These examples highlight plasma's remarkable diversity and power. Witness the sun's fiery eruptions as streams of hot plasma surge into space. This captivating display reveals the raw intensity of thermal plasma in motion. Building on the plasma and ionization discussions, the next phase shifts to experimental applications. One such application is the wireless indicator light, which serves as a simple yet effective method for detecting electromagnetic fields, illuminating when exposed to sufficient energy. High-frequency solid-state Tesla coils benefit from wireless indicators over wired solutions. Instead of LEDs, I chose the General Electric NE42 neon glow lamp, widely used since the 1970s. This lamp, filled with neon gas and paired with a hand-wound coil, lights up near the oscillator, responding to electromagnetic energy, just as Heinrich Hertz's 1887 spark gap detector demonstrated wave propagation through induced glow. Raising the globe 8 centimeters above its intended position, I begin charging its outer surface through triboelectric effects, where friction transfers electrons between materials. This initiates a cloud-like glow in the rarefied xenon gas. Although the increased distance reduces magnetic field strength, the gas maintains its luminous state, not solely through ionization, but also through electron excitation. The alternating electric field does not fully strip electrons from atoms, but lifts them to higher energy states. As they return to their ground states, they release photons, producing a bluish-white glow. This shows how excitation-induced emission can sustain visible glow even without full ionization, highlighting the interplay between electromagnetic forces and triboelectric charging. Plasma formations shift dynamically in response to electromagnetic field strength. Initially, with the globe resting on the coil, a weakly defined toroid appears, formed by the strongest magnetic field at the coil's surface. As the globe is raised, the magnetic field weakens, while the electric field remains sufficient to sustain plasma. This results in the emergence of filamentary plasmoids, thread-like plasma structures, shaped by nonlinear streamers and evolving field interactions. Filamentary plasmoids share characteristics with streamers, which form when the electric field around charged particles accelerates free electrons to energies sufficient for ionizing atoms through collisions, creating a chain reaction of ionization. These structures develop dynamically within the plasma environment, responding to field fluctuations, Raising the globe even farther reduces the magnetic field's influence, and the filamentary plasmoids transition into an amorphous globe, a diffuse plasma state where electric field excitation dominates while magnetic confinement diminishes. Notably, introducing a conductive path, such as touching the globe, alters the electric field distribution. Despite Pyrex being an insulator, its surface can still interact with the field, allowing streamers to reshape into a toroid. Reversing this sequence, gradually lowering the globe strengthens the magnetic field, driving the plasma formations back through filamentary plasmoids and ultimately restoring the toroid when the globe is placed directly on the coil. This progression illustrates how plasma behavior is shaped by the balance of electromagnetic forces. With the globe positioned at the lowest point of the load coil, as specified by the vendor ModeRock, plasma initiation occurs without introducing any surface charge. The rarefied xenon gas interacts dynamically with the electromagnetic conditions created by the oscillator, resulting in the appearance of the toroid. This plasma structure remains still and stable despite the system's underlying electromagnetic activity, demonstrating how electromagnetic interactions alone can lead to such formations within small volumes. The photo presents the high-frequency solid-state Tesla coil or Tesla gun, positioned atop a spark gap Tesla coil for size comparison. The spark gap Tesla coil operates at 500 kHz, highlighting the contrast between the two systems. In the next video, the Tesla gun will be used to charge the xenon gas inside the globe, initiating plasma formation. In this demonstration, the Tesla gun charges the surface of the globe, forming a toroid in the rarefied xenon gas. Initially stable, the toroid becomes unstable as conditions in the electromagnetic field change. This instability produces a distinctive squealing sound. The sound arises from rapid oscillations and instabilities in the electromagnetic field. As the toroid breaks down, these oscillations lead to fluctuating ion densities and currents within the plasma, creating pressure waves in the surrounding medium. These pressure waves are perceived as the squealing sound, representing the dynamic interplay between the plasma and the electromagnetic field during toroid instability. This demonstration compares a 1-liter globe to the original 0.3-liter ModeRock globe presented in panel 44, highlighting differences in toroid stability. While both globes support plasma formation, the larger volume alters electromagnetic field distribution, influencing plasma behavior. The toroid in the 1-liter globe exhibits instability, accompanied by a squealing sound occurring at approximately 2 cycles per second. This acoustic effect arises from rapid oscillations in ion density and electric currents within the plasma, generating pressure waves in the surrounding medium. Beyond its instability, the toroid shape is governed by magnetic fields created by moving charges within the plasma. These fields naturally form closed loops or toroidal structures as plasma currents interact with the surrounding electromagnetic forces. Additionally, the toroid exhibits rising motion due to buoyancy effects, since plasma is likely less dense than the surrounding gas. Thermal influences also contribute, as heated plasma becomes less dense than cooler gas, driving its upward movement within the globe. As electromagnetic conditions fluctuate, the toroid structure repeatedly destabilizes, emphasizing how field strength, globe size, and gas pressure collectively shape plasma behavior. The ModeRock device was redesigned to house a 2-liter borosilicate globe, doubling the original diameter. This modification enabled plasma formation studies on a larger scale, expanding beyond the previous 80 mm globe. To analyze the oscillator's resonance frequency, I estimated the inductance of the original 18-gauge air core coil using Wheeler's formula. Wireless frequency measurements with a Yaesu transceiver provided capacitance estimates, bypassing the protected printed circuit board, or PCB, without direct access. A new load coil of insulated 12-gauge solid copper wire was constructed to match the larger setup. Its inductance was calculated using Wheeler's formula, and its resonance frequency was measured by precisely tuning the Yaesu transceiver. This ensured accurate detection of the tank circuit's resonant frequency with the new coil, verifying that it remained within a small tolerance of the ModeRock oscillator's original 18-gauge coil. By maintaining this frequency alignment, impedance mismatch was minimized, optimizing energy transfer efficiency. Additionally, the 12-gauge wire's insulation should comfortably withstand 3 kV breakdown under normal humidity conditions, which ranged from 24% to 55% at the time of my experiments. Now, the emphasis on precise tuning explicitly ties to the transceiver's role in measuring resonance frequency rather than the coil itself. Detailed calculations for self-inductance, capacitance, turn count, and voltage breakdown are provided at the end of this video. The photo features the Yaesu FTDX10 high-frequency transceiver paired with a small insulated wire antenna alongside UHF and BNC connectors. It illustrates how the antenna connects to the transceiver, enabling precise wireless frequency measurements for oscillator analysis while bypassing the protected printed circuit board. To ensure accurate readings without overloading the receiver, I carefully optimized the antenna setup and adjusted receiver functions, allowing controlled signal reception while preserving sensitivity to oscillator frequencies and minimizing interference from background signals. Using the Yaesu FTDX10 transceiver's 3D spectrum screen, I analyzed the resonance frequency of the ModeRock oscillator to identify harmonics and multiple resonant frequencies. The transceiver offers wireless monitoring, preferred over an oscilloscope for its detailed spectral analysis, high sensitivity, and safe operation, features that are invaluable for coil design and plasma experiments. The 3D spectrum display visualizes frequency along the x-axis, signal strength along the y-axis, and time evolution along the z-axis. The z-axis provides a real-time history of signals, showing activity up to 1 second earlier, even when the ModeRock oscillator is off. For high-frequency RF radiation near 10 MHz, CW modes like CWL and CWU are most effective. These modes toggle the carrier to produce RF energy bursts, enabling precise narrowband frequency identification. In CWL and CWU modes, the carrier frequency is offset by the chosen tone, lowered in CWL and raised in CWU. Incoming signals form a beat note, heard as a steady tone, but oscillator harmonics and frequency mixing add complexity to the transceiver's audio output. The Yaesu transceiver pinpointed the oscillator's 10.065 MHz resonance, demonstrating its precision in frequency analysis. Now, the resonance frequency of the oscillator is known, and as we saw earlier, we can calculate the inductance of the ModeRock coil using Wheeler's formula. Given these two values, we can calculate the capacitance of the oscillator LC circuit. The expression for capacitance is an approximation because it relies on idealized assumptions, estimated coil inductance, and potentially imperfect measurements of resonance frequency. You can view the detailed calculations at the end of this video. In summary, the resonance frequency L was measured to be 10.065 MHz. The coil inductance is calculated to be 2.77 microhenry, and the capacitance approximated to be 90.20 picofarad. To accommodate the 2-liter globe, I begin modifying the setup by removing the existing 18-gauge magnet wire. Initially, I try unwinding it, but cutting the wire first proves more efficient. Adapting my approach, I make the cut, allowing for smoother extraction from the oscillator housing. This adjustment optimizes electromagnetic field distribution and resonance tuning in the scaled-up experiment. With the coil removed, the foundation is set for integrating a redesigned winding structure to enhance plasma dynamics within the larger borosilicate globe. To optimize the coil for the larger borosilicate globe, I wind several turns of 12-gauge insulated wire around an acrylic mandrel. Placing the mandrel horizontally ensures stability, while securing the wire's end maintains tension. I roll 3 turns, keeping spacing uniform, and leave an extra length for oscillator housing connection. This process fine-tunes electromagnetic field interactions and resonance, preparing the coil for plasma experimentation. A Lego-based harness stabilizes the 3-turn air core coil, supporting the 2-liter borosilicate globe while ensuring precise spacing. The modular design enhances durability, insulation, and electromagnetic field uniformity. A schematic illustrates the setup, and a photo highlights the spacer's alignment role, optimizing plasma experimentation. This video showcases the fully assembled 3-turn 12-gauge coil, secured by a custom Lego harness for precise alignment and stability. To enhance adaptability, 18-gauge stranded wire connects the coil to the oscillator terminals using crimp disconnects for secure adjustments. The setup smoothly rotates, offering a 360-degree view of coil integration, spacing, and connections. Designed for optimal electromagnetic field distribution, this configuration supports precise plasma excitation and improved experimental accuracy. This experiment validates the calculations used to design the larger diameter load coil, assessing its impact on plasma formation and resonance behavior. The 2-liter borosilicate globe, nested within the newly won 12-gauge 150mm diameter coil, is energized using the ModeRock oscillator. As the Tesla gun charges the globe, a toroid plasma emerges, later evolving into filamentary plasmoids, demonstrating dynamic electromagnetic interactions. Simultaneously, the Yaesu FTDX10 transceiver's 3-dimensional spectrum screen, or 3DSS, on the HP monitor reveals real-time spectral frequencies as thin red lines, visually mapping the oscillator's harmonic structure. Scanning a 20 kHz span, I identify the highest spectral density, a frequency domain fingerprint revealing key resonant frequencies. When the oscillator switches off, the frequency spectra turn blue, receding along the z-axis, illustrating signal decay over time. Beyond visual frequency tracking, an audible signal aids measurement. CW mode transmissions, pure sine waves in Morse code, contrast sharply with the ModeRock oscillator's harmonics-rich output, which produces nonlinear switching noise, widening the signal's bandwidth. The transceiver demodulates this signal, generating complex audio output due to frequency beating effects. Repeating this process 3 times, I confirm measured resonance frequencies of 10.447 MHz, 10.450 MHz, and 10.451 MHz, all within expected parameters. Since the CWL side tone is set at 1000 Hz, well within the measured frequency range, further side tone adjustments are unnecessary. This test provides critical confirmation of the coil's efficiency, ensuring precise electromagnetic tuning for subsequent plasma experiments. As the ModeRock oscillator powers on, the Tesla gun energizes the borosilicate globe, exciting rarefied xenon gas. A toroid plasma forms, shaped by electromagnetic forces, but remains unstable, shifting due to ionization effects. Near the experiment's end, I introduce a change, placing both hands around the globe. This collapses the toroid into filamentary plasmoids. Weaving dynamically, my hands act as capacitive couplers, altering surface potential in the electric field, triggering plasma beads, bright spots along streamers. These micro-discharges fluctuate with field variations. Filaments adjust, seeking equilibrium. This illustrates plasma's sensitivity to field changes and its evolving behavior. The next few panels contain programmatic code for calculations needed for designing a larger diameter coil. Given parameters of the ModeRock oscillator 18-gauge coil and resonance frequency of this ICP device, to design a coil that matches the 80 mm ModeRock oscillator, I first calculated its self-inductance, ensuring it would operate at the intended resonance frequency. Using Wheeler's formula, I estimated the inductance of the original 18-gauge air core coil, establishing a reference point. This equation, specifically tailored for single-layer solenoid coils, provided a reliable inductance value based on coil dimensions and turn count. For the new 12-gauge insulated copper coil, I applied Wheeler's formula again, adjusting for the increased conductor thickness and modified coil geometry. The result ensured resonance alignment, minimizing impedance mismatch, while optimizing energy transfer for stable plasmoid formation. With inductance values established, I needed to determine tank circuit capacitance to fine-tune resonance frequency. Since direct access to the oscillator's protected PCB was restricted, I measured capacitance wirelessly using a Yaesu transceiver. By detecting peak resonance frequency and knowing the coil's inductance, I applied standard LC resonance equations to estimate capacitance. Matching capacitance to the coil ensured energy storage efficiency within the tank circuit, reinforcing controlled plasma oscillations while maintaining frequency stability. To design the replacement coil for the ModeRock oscillator, I first determined the required number of turns to achieve the desired inductance, ensuring resonance compatibility with the tank circuit. Applying Wheeler's formula, which provides inductance estimates for single-layer air core coils based on diameter, turn count, and wire gauge, I calculated the inductance for the new 150 mm coil. Adjustments were made to optimize energy transfer and maintain impedance matching with the oscillator circuit. Once the inductance was determined, I validated the design by calculating the oscillator's eigenfrequency using the standard LC resonance equation. Substituting the calculated inductance and the estimated capacitance of the ModeRock tank circuit, I backsolved for the expected resonance frequency. The resulting frequency remained within a narrow tolerance of the original oscillator specifications, confirming that the coil redesign maintains stable resonance while ensuring efficient plasmoid formation. Beyond inductance and capacitance, ensuring voltage breakdown resilience is critical for coil integrity in high-energy conditions. Using material specifications, I confirmed that the insulation on the 12-gauge wire could withstand up to 3 kV, preventing premature electrical breakdown and unwanted discharge losses. At normal humidity levels 40 to 55%, this dielectric strength ensures stable energy transfer while maintaining precise plasmoid formation. The estimated breakdown voltage is 3000 gap millimeter, where gap millimeter refers to the breakdown voltage per millimeter of insulation thickness. This unit expresses the dielectric strength of the material, indicating how much voltage per millimeter the insulation can endure before electrical failure occurs. By maintaining sufficient insulation thickness, the coil remains protected, ensuring efficient plasmoid formation without unintended discharge pathways.